Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Heliosphere, the Sun's expansive shield. The heliosphere is a vast bubble of charged particles and magnetic fields created by the Sun, stretching far beyond the outer planets of our solar system. It acts as a protective shield, defending the solar system from the majority of cosmic rays and interstellar particles that permeate the galaxy. To understand the heliosphere is to embark on a journey from the Sun's core to the very edge of its influence, tracing the flow of solar wind, the dynamics of magnetic fields, and the interplay between our solar system and the wider universe. At the heart of the heliosphere lies the Sun, a massive ball of hydrogen and helium undergoing nuclear fusion. This process generates the immense energy that powers the Sun, producing light and heat that sustain life on Earth. But the Sun's influence extends far beyond visible light and warmth. It continuously emits a stream of charged particles known as the solar wind. This wind, composed mainly of electrons and protons, flows outward in all directions, carrying with it the Sun's magnetic field. The solar wind originates in the Sun's corona, the outermost layer of its atmosphere, where temperatures reach millions of degrees Celsius. These extreme temperatures cause the solar material to become ionized, meaning the atoms lose electrons and become charged particles. Driven by the high pressure of the corona, these particles accelerate away from the Sun, escaping its gravitational pull and forming the solar wind. As the solar wind travels outward, it carries the Sun's magnetic field, creating what is known as the Interplanetary Magnetic Field, IMF. This magnetic field, twisted into a spiral shape by the rotation of the Sun, influences the behavior of the solar wind and the heliosphere as a whole. The strength and structure of the IMF play a crucial role in shaping the boundaries of the heliosphere and its interactions with interstellar space. The boundary of the heliosphere is not a fixed, rigid surface but rather a dynamic region shaped by the pressure balance between the solar wind and the interstellar medium. The interstellar medium is the tenuous mix of gas, dust, and cosmic rays that fills the space between stars in our galaxy. As the solar wind pushes outward, it creates a bubble within this medium, with the outermost layer being the heliopause, the point where the pressure of the solar wind is balanced by the pressure of the interstellar medium. Before reaching the heliopause, the solar wind encounters a region known as the termination shock. Here, the solar wind slows down abruptly as it begins to interact with the interstellar medium. This interaction creates a turbulent region filled with shock waves and energetic particles. The exact location of the termination shock varies with solar activity, moving closer to or farther from the Sun depending on the intensity of the solar wind. Beyond the termination shock lies the heliosheath, a broad region where the solar wind slows down further and becomes more turbulent. In this region, the solar wind is deflected and heated as it pushes against the interstellar medium. The heliosheath is a complex and dynamic area, influenced by variations in both solar activity and the properties of the interstellar medium. Finally, at the outermost edge of the heliosphere, we reach the heliopause. This boundary marks the limit of the Sun's influence, where the solar wind pressure is balanced by the pressure of the interstellar medium. Beyond the heliopause lies interstellar space, where the environment is dominated by particles and fields from other stars in the galaxy. The study of the heliosphere and its boundaries has been a key focus of space exploration for decades. One of the most significant missions dedicated to this purpose is NASA's Voyager program. Launched in 1977, the twin Voyager spacecraft, Voyager 1 and Voyager 2, were initially designed to explore the outer planets. However, their missions were extended to study the outer reaches of the heliosphere and beyond. Voyager 1 crossed the termination shock in December 2004, followed by Voyager 2 in August 2007. These encounters provided valuable data on the structure and dynamics of the termination shock, revealing the complex interactions between the solar wind and the interstellar medium. Voyager 1 eventually crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed suit in November 2018, providing further insights into the nature of this boundary and the conditions in the heliosheath. The data collected by the Voyager spacecraft have revolutionized our understanding of the heliosphere and its interactions with interstellar space. They have revealed that the heliosphere is not a symmetric bubble but rather an elongated, teardrop-shaped region, with a tail extending downstream from the Sun's motion through the galaxy. This shape is influenced by the motion of the solar system through the interstellar medium and the varying pressure of the solar wind. In addition to the Voyager missions, other spacecraft have contributed to our knowledge of the heliosphere. The Interstellar Boundary Explorer, IBEX, launched by NASA in 2008, has provided detailed maps of the interactions at the edge of the heliosphere. IBEX detects energetic neutral atoms, ENAs, that are created when charged particles from the solar wind and the interstellar medium exchange electrons. These ENAs travel back toward the inner solar system, where they can be detected and used to infer the structure and dynamics of the heliosphere's boundaries. Another important mission is the Solar and Terrestrial Relations Observatory, STEREO, consisting of two nearly identical spacecraft launched in 2006. STEREO's primary mission is to study the Sun and its effects on the solar system, but its observations also contribute to our understanding of the solar wind and the heliosphere. By providing a stereoscopic view of the Sun and the solar wind, STEREO helps scientists understand the three-dimensional structure and dynamics of these phenomena. The study of the heliosphere is not only of scientific interest but also of practical importance. The heliosphere acts as a protective shield, deflecting many of the high-energy cosmic rays that would otherwise bombard the solar system. These cosmic rays can pose a significant threat to both astronauts and spacecraft, as well as to life on Earth. Understanding the heliosphere and its ability to shield us from cosmic rays is crucial for the safety of future space missions and for assessing the potential risks to our planet. One of the key questions in heliospheric science is how the heliosphere interacts with the interstellar medium and how it evolves over time. The properties of the interstellar medium, such as its density, temperature, and magnetic field strength, can vary significantly, and these variations can influence the shape and size of the heliosphere. Additionally, the solar wind itself is not constant but varies with the 11-year solar cycle, causing the heliosphere to expand and contract over time. To gain a better understanding of these interactions and variations, scientists are developing sophisticated models of the heliosphere and the interstellar medium. These models incorporate data from spacecraft observations, ground-based measurements, and theoretical studies to simulate the behavior of the solar wind, the interstellar medium, and the resulting heliospheric boundaries. These models are essential for predicting how the heliosphere will respond to changes in solar activity and interstellar conditions. One of the most exciting frontiers in heliospheric science is the study of the local interstellar medium, the region of space just outside the heliosphere. This region is influenced by the collective winds and radiation from nearby stars, as well as by remnants of past supernovae. Studying the local interstellar medium can provide insights into the broader galactic environment and the history of our solar system's interactions with it. Recent observations from the Voyager spacecraft, IBEX, and other missions suggest that the local interstellar medium is not uniform but contains structures such as clouds and magnetic filaments. These structures can interact with the heliosphere, causing variations in its shape and dynamics. Understanding these interactions is crucial for building a comprehensive picture of the heliosphere and its place in the galaxy. As our understanding of the heliosphere and its boundaries continues to evolve, new missions are being proposed to explore these regions in greater detail. One such mission is the Interstellar Probe, a concept for a spacecraft that would travel far beyond the heliopause to directly sample the interstellar medium. This mission would provide unprecedented data on the properties of the interstellar environment and its interactions with the heliosphere. Another exciting development is the proposed solar wind electrons alphas and protons (SWEAP) investigation, part of NASA's Parker Solar Probe mission. Launched in 2018, Parker Solar Probe is designed to study the Sun's corona and the solar wind up close, providing valuable data on the processes that drive the solar wind and shape the heliosphere. SWEAP's instruments will measure the properties of the solar wind particles, helping scientists understand how the solar wind is accelerated and how it evolves as it travels outward. In addition to these missions, advances in ground-based and space-based telescopes will continue to enhance our understanding of the heliosphere and the interstellar medium. Observations of cosmic rays, energetic particles, and electromagnetic emissions from these regions provide valuable clues about their properties and dynamics. These observations, combined with data from spacecraft and theoretical models, will help scientists build a more complete and detailed picture of the heliosphere and its interactions with the galaxy. The study of the heliosphere is a testament to humanity's enduring curiosity and quest for knowledge. From the early observations of the solar wind to the groundbreaking discoveries of the Voyager spacecraft, each step in our exploration of the heliosphere has expanded our understanding of the Sun's influence and our place in the universe. As we continue to push the boundaries of space exploration, the Heliosphere remains a key frontier, offering new insights into the nature of our solar system and its interactions with the broader cosmos. The Heliosphere is a dynamic and ever-changing region, shaped by the interplay between the solar wind and the interstellar medium. Its study requires a multidisciplinary approach, combining observations from spacecraft, ground-based measurements, and theoretical models. As we continue to explore and understand the Heliosphere, we uncover new mysteries and deepen our understanding of the cosmos. The Heliosphere's importance extends beyond mere scientific curiosity. It is a crucial aspect of the solar system's architecture, influencing everything from cosmic radiation levels to the potential habitability of planets. The Heliosphere embodies the dynamic relationship between our star and the vast interstellar space, a relationship that shapes the very environment in which our solar system exists. The study of the Heliosphere not only enhances our comprehension of solar and cosmic processes but also fortifies our preparation for future space endeavors. From the early days of solar wind detection to the boundary-breaking voyages of the Voyager probes, our journey through the Heliosphere has been one of awe and revelation. Each new piece of data brings us closer to understanding the protective bubble that envelopes our solar system, a bubble that has shielded us for billions of years. The Heliosphere, with its intricate dance of particles and fields, remains one of the most fascinating subjects in our quest to understand the universe.